It's the size of the universe. The bit we can see, which is what's called the observable universe, has about between 1 and 2 trillion galaxies in it, depending on how you know, little tiny galaxies and big galaxies, but it's let's say a trillion-ish, something like that. And that is only a small patch of the universe that exists, so we're sure of that. Whether the universe is infinite in all directions, we don't actually know, but as far as we can tell, it could be. So my favourite fact about the universe is that it might be infinitely big.
The question isn't about whether dark matter exists or not. What's going on is when we measure gravity in the universe, the collective gravity of the stars, the planets, the moons, the gas clouds, the black holes, the whole galaxy, 85% has no known origin. It's not a matter of whether dark matter exists or not. It's a measurement, period. Dark matter is not even what we should be calling it, because that implies that it's matter. It implies we know something about it that we actually don't. So a more precise labeling for it would be dark gravity. Now, if I called it dark gravity, are you going to say, does dark gravity really exist? I'd say, yeah, because 85% of the gravity has no known origin. There it is. So here's how you actually measure the stuff. In a galaxy, which is the smallest aggregation of matter where dark matter manifests. So you look how fast it's rotating, and we know from laws of gravity, you write down these equations, say, oh, look how fast it's rotating, invoke that rotation rate in the equation, and out the other side says how much gravity, how much mass should be there attracting you. And the more mass that's there, the faster we expect you to be orbiting. That kind of makes sense. So when you do this calculation on a galactic scale, we get vastly more mass attracting you than we actually can detect. I'm adding up stars, gas clouds, moons, planets, black holes. Add it all up. It's a fraction of what we know is attracting you in this orbit. And we cannot detect the rest. And so we hand it this title, dark matter. Understandably, I suppose, but it implies that we know that it's matter. But we don't. We know we can't detect it in any known way, and we know it has gravity. So it really should be called dark gravity.
It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared, so sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, 350 billion galaxies in it, in less than a millionths of a second. So a very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know. Is time travel possible? Great question. It's kind of obvious to say it's possible into the future, because of course that's what we're doing. We're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1g, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda galaxy, and then, which is 2 million light years away from from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey. And you could do that calculation. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905. It's not even the theory of gravity. So time travel is possible into the future, and it's inevitable that you travel into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around.
If you walk in the rain, the only part of you that's getting wet is the part that's falling directly on top of you, so your shoulders and the top of your head. So you get that area, right, and you look at the raindrops per minute that's hitting that area and how fast you're walking across the street. You can calculate that and get a total number of raindrops that you hit if you go slowly. Now, if you run, rain is still going to hit you on your head and shoulders, but for not as long.
Right.
But now you have your entire surface area of the front of your body that's running into falling raindrops. Have you ever seen off-ramps to freeways? So, off-ramps, have you noticed they have grooves in them? Okay. That's to prevent you from sliding off if the road is a little bit slippery because it just rained or whatever. They groove the off-ramp, a curved off-ramp. So you say, who invented those grooves? That's brilliant. It's simple and brilliant. NASA did. NASA. All right. Why? Because the space shuttle, which comes in for a landing, does not have engines. All right. It is a glider as it comes in for a landing, and it's got a parachute, and it's got some brakes, but it's really got, so if there's a crosswind, that's hard to fight that. So those grooves help it stay on track, because it doesn't matter how you come in, the photo at the end shows how good a steerer you were at. So some clever engineers decide if you groove it, then the shuttle can stay on course more tightly, and that was then borrowed for the freeway system.
Why is time different on different planets, like in Interstellar? So that's an easy question to answer. It's Einstein's theory of general relativity. As you come closer to a planet, then your time, so let's say you have a watch and you look at the watch, then you'll see the watch tick at the normal rate, 1 second per second, and you won't see anything unusual. But from the perspective of someone far away, that watch will be ticking more slowly than their watch. And it's really to do with the distortion of space and time in the vicinity of the planet. So the general rule is if you go to something that's very massive, so you approach a very massive planet or even a black hole, then as you go there, from the point of view of someone far away, they will see your time tick more slowly. So that's I was going to say basic general relativity. Should we leave it at that? That's it. Everybody should know what a black hole looks like. So a black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. And if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape the gravitational pull of a black hole. But another description of the event horizon, which confused people all the way through the history of black hole research actually, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. Now that's a direct prediction of Einstein's theory of relativity from the external perspective. There is a central problem, though, which is still not solved, which is what lies at the center of the black hole. You might think of it as an infinitely dense point to which this massive star collapses. So what are we picturing? It's this thing called the singularity. Actually, it's not right to talk about the center of a black hole, really. Just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that space and time are so distorted that in some sense their roles swap. The singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. But the nature of that thing was not and is still not understood.